get into we're going to take care of, I'll just tell you what's coming up today. We're going to do, finish up the halfwave dipole, talk about monopoles, and then do array antennas. And if we can, we'll do the receiving circuit and an antenna free synergy equation. But arrays takes some time. All right. Let's see what else. First, are there any questions at all? I put the answers, I think, and the solutions up on OneNote. If you take a look now. Ooh, wait a second. There may be. I may put them. I've got them on OneNote, but I'm not sure I copied those into your OneNote folder. You can check and tell me. If you don't have the solutions, I'll put them in. Just send me an email and make sure. I don't think I did copy. All right. So now, back to, let me just finish up the half-wave dipole. The real key, in my opinion, always is going to be directivity / gain and the radiation resistance. Now, I'm going to talk just for a second about the true input impedance of the half-wave dipole. So this is going to be for a half-wave dipole. And we have a half-wave dipole as such. There's going to be some R input or Z input. It's the input impedance of this. And this is assumed lambda over 2 long. Theta is always measured from the z-axis, by the way. It's not measured from the 90-degree point. So when we do this, for half-wave dipole, the actual directivity, assuming it's aligned in the z direction, this would be the z-axis. Directivity as a function of angle is equal to 1.64. Didn't I put that down there for maximum directivity for a half-wave dipole? I showed you general equation for half-wave dipole, or for arbitrarily long dipole, how to get the electric fields from it, then from the electric field, how you would get the normalized power density. From that, how you get the directivity and such. For the half-wave dipole, it has a maximum value of 1.64. And then it's going to be times the cosine of pi over 2 cosine of theta over the sine of theta squared. Do y'all remember that? That's one you'll see over and over again for half-wave dipole. Now, a short dipole, it's got a sine squared theta variation of Dmax, right? This is for a half-wave dipole. Then you can put a d lambda over 2. This is in the book. D short dipole is just 1.5 or 3/2 times the sine squared of theta. Do y'all remember that? This would be for the short one, right? That would be for the half-wave, right? Now, a couple other things I'm going to say about this. These two are actually very similar. The difference between 1.64 and 1.5, not much. And you're going to find this too. The difference between this angular variation and this one, not much. If you looked and you plotted the actual, if this was the short dipole right here, and you looked at directivity as a function of angle, you get that, and if you place and you did the half-wave, it would be just a little bit tighter, but not much. You'd actually see about like this. be a little bit further out because you'd have a peak value of 1.64 at 90 degrees. Be a little bit narrower, but not much. As a matter of fact, not a whole lot of difference. Here's where the real difference lies. When you talk about the radiation resistance or the impedance, the input impedance and the radiation resistance. So the input impedance is actually equal to the radiation resistance of the antenna plus J, the reactance of the antenna. And they usually put it A and T here. So for a half-wave dipole, Zn for lambda over 2 dipole is 73.2 ohms plus J 42.5 ohms. Now that's in his book. So this is important. The radiation resistance for half-wave dipole is 73 ohms, roughly. And if you compare that to a short dipole, they don't even put the reactance down in Dr. Wentworth's book, but there is a reactance. In other words, it's not zero, but the radiation resistance, this would be the radiation resistance, and that's why we use half-wave dipoles. The radiation resistance is much, much better, so for less current, we get a lot more power, a lot less current. And, it takes a lot less current to get the same amount of power as if it was short. For a short dipole, they just put the radiation resistance in Dr. Wentworth's book, and that's 40 times pi squared length over lambda squared. Do y'all remember that? Right? All right, and for this one, if you look, remember, you use this formula for the radiation resistance. This would be for a short dipole. I'm trying to put everything for half dipole up here, and this would be short dipole. Remember, the condition is L is less than lambda over 10. So the greatest this could be, if you think about it, if L was lambda over 10 divided by lambda, that would be 1/10. Square that, you get 1/100th. Times 40, right? It's 4 over 10, or 0.4 pi squared. And think about that. 0.4 pi squared. Pi is about 3.14159. Squared about 10, so it's about 4 ohms. Do you all see that? That's horrible, all right? If you have 1 amp there, you get 4 watts out. If you have 1 amp with into a half-wave dipole at 73 ohms, right? You get 73 point something watts out. You get a whole lot more. That's my point. Same current, input impedance is just different, all right? That's the reason. And not only that, I don't show you this, but the reactance for, if you actually had Z input for a short wave, or I mean for a short dipole, it would be this for the radiation resistance, but there would be a reactance there that's dominant, I believe. It's proportionally much greater than 42.5. Yeah.
I think I have 80 pi squared.
That's for the what?
For short dipole.
That's not the radiation resistance. Or I'm sorry, you're right. You are so right. That's my.
I think the power is
Yeah, you're absolutely right. It's 80 because of the 1/2. My bad. I apologize. 80 pi squared times L over lambda squared. It should be that. And 40 pi squared, and then it's L over lambda squared times I squared. Yeah, my bad. Thank you so much. That was a mistake. All right. Anyway, the real thing is, so it would be 8 ohms. This is for the max. This thing's super small. And it's typical, you can get values of 1/20th lambda, 1/50th lambda, so just remember that. Now, the real thing is this, that the reactance of this too is pretty high. So there's a lot of reactive power stored. In other words, it's a big waste, all right? We would like this thing to be 0. And that's what we would like, this thing to be 0. And now I'm going to tell you how they do it. All right. so this is all for a half wave antenna exactly. Now, if you put the length of an antenna, write this down, to be 0.485 lambda. And I'm going to make, this is kind of true, and I'll explain that in a second. This isn't exactly true, and I got to tell you, because the wire radius does have a bearing about what I'm about to tell you. Usually they assume they're extremely thin, they're thin antennas, but they actually have to use thicker antennas if they're transmitting a lot of power. So you're going to just have to trust me on what I'm about to tell you. So in Dr. Whitmore's book, he says if we make the length of this antenna, L, equal to just a little bit less than 0.5 lambda. Instead of 0.5, it's 0.485, right? So it's a couple of percent shorter. Well, then your input resistance, Zn input, is equal to about 73 ohms plus J0. They get rid of the reactive component entirely. Now, the real truth is this. Wire radius makes a difference in the input impedance of an antenna, as well as the frequency it's operating at. Remember how we talked about skin depth and the currents hug the surface? Well, the higher the frequency, the less depth of penetration, the more they hug the surface. And it also causes a slight difference in the actual radiation resistance and reactance. Now, if you cut it down to 0.485, if it's a very, very thin wire antenna, I believe that'll get about 73 ohms. The truth is, if you just took say you take a coat hanger and you undo it, straighten it up, cut off the, the frayed part, and then you take that thing, break it halfway in the middle and bend the center point, and you measure the impedance, assume you are driving it such that the frequency is a half wavelength or whatever's left. Well, if it's exactly a half wavelength, then you're going to get about half as much reactance as you are resistance. In other words, whatever this part, it's not exactly, whatever this part is, this thing will be about half, a little more than half, all right? About half. Now, if you take a pair of wire cutters and you start knocking off a little bit of both sides, just knocking it down a little, you'll see this reactance right here dropping. And eventually it'll hit about 0, all right? Now, if you keep shortening it and you go down to a point like 4.6 lambda, then you'll start getting a minus J something. All right, so it'll go from an inductor to a capacitive reactance, I believe. I've never actually done the thing that I'm talking about. I really haven't. I know you can take fingernail clippers. You can just take real thin wire and do this with a yardstick and start clipping off the ends with fingernail clippers of the wire, like you would fishing line, and bring it down a little, and you'll see something like this. I've never done it myself, but I know you can do it. One thing I do know is length plays a role in getting no reactance. Now, the reason this thing is bad, because now it takes more voltage to get the same amount of current. Remember, the power is all I squared R here. It's 1/2 I squared times this resistance is how much power you launch. This doesn't help us launch power. So you want to get rid of the reactance. A way you can do it with some antennas that you can't modify to get rid of it, you're going to put a matching network. If there's a J42.5, then I'll put a capacitor in series with that that'll have a reactance of minus J42.5 and get rid of it that way, all right? But you never want to put more, you never want reactance, any kind of plus or minus J reactance on anything that you're driving to launch power ever, all right? Now, near field energy is different, but we don't care about near field energy. We're launching stuff. And this is the thing I wanted to talk about. When it's 0.485, then you get this. And by the way, the directivity doesn't change at all. The directivity is the same as if you cut it down, and the electric fields are the same, the H fields and such. Got it, everyone? That's real, real important. Okay. Now next, in the real world, I'd say most of the time that you're dealing with power, like broadcast antennas, things like that, you're not actually dealing with with dipoles, you're dealing with monopoles, where they have only half the antenna above a ground plane. Now I want to get into this. Y'all know like car antennas, the old aerials that were just straight up? They were the real antennas, the full, if you took that wire and put it below there, that's how big they'd be. But I've got to go through imaging to show you how, in fact, a conducting ground will create an image of the upper current. So if we wanted the same electric fields and stuff from an antenna that will, from a half wave antenna, it will only have to be a quarter wavelength long. I'm about to show you why, and this is kind of interesting. I don't know the first person that actually found this out. So first, if we have a ground plane here, I always think of copper or something like that, gold. Copper's perfect because you're familiar with copper. Copper's a very good conductor, right? Well, if you have a sheet of copper down, and you put a plus charge, plus Q at a height, H above that. Now, you can go ahead if you wanted to, and if you want it, say it was static, all right? If you wanted to find the electric fields at a given distance R away, not electric fields, say voltage, for starters up here at a given distance R away, you could solve del squared of V is equal to 0 outside this area, right? And then you could put the singularity there. And all down here would be 0 volts. Do y'all follow me? That's ground. It's a pain in the butt to do that. Or you could do something that'll solve the problem without ever solving this differential equation, this del squared equation. You could simply put, if this is a plus Q, you could come down a distance H, and you could put a minus Q. Then you would assume the ground plane doesn't exist. Do y'all follow me? And then you would get the voltage or electric fields, either one. You could get, let's call this R plus, call this R minus. And what you would end up doing if you want electric fields, you get the electric fields from the plus charge. And then you would get the electric fields from the minus charge, and the sum of these two would be the net electric field. Y'all follow me? How many have had method of images? Can you make one you didn't get it, really? Well, this is the method of images. What it does, in physics, I don't know, I guess they show that in higher levels courses. The first time I ever saw this, I think it was in my EMAG class when I was a sophomore/junior. And then in my senior level course, senior/graduate school, I had a course that dealt specifically with solving electrostatic and electrodynamic problems from the differential equations point of view. And this is a big deal because solving that del squared of V equals 0 business there, that's a pain in the butt. You've got a series solution that asymptotically approaches what I'm showing you here, all right? Now, that would be the E field, but you could also say that the voltage here would be the voltage from this charge as if at infinity the voltage was 0, plus the voltage from this charge. And there would be two different distances, okay? So you can do that. But here's the neat thing about this. So this method of images works this way. Then, if you have a current, and I'm going to try to do this. Suppose I have a current like this, I, and it's got a length L, and it's at a height H above a perfect conducting plane. Now, say it's a wire, right? Here's the way we kind of reason through this. You can say, really, this thing is collecting positive charge. And it's losing charge down here, so it's got a negative charge setting. If you think of it this way, it should make sense. Kind of makes sense, right? All right. If you think about the method of images, I come down a distance h below this, and I'll put, where that minus is, now I put a plus q. And I come down here, and where that plus q is, I put a minus q. You all with me on that? Now, without going through it bit by bit all the way through here, you all see how it looks like an image current would be induced that would be in the opposite direction. You all see that? This is important. The point I'm going to make is, if the current is parallel to a perfect conducting plane, its image will be in the opposite direction, same magnitude, at the depth equal to the height that the other one's above the plane. You'll see why I'm doing this. And by the way, you know, EMAG, when I teach EMC, the electromagnetic compatibility and compliance course and interference course, we go through, this becomes a real deal because I just want to mention this. Did I give you the spiel about EMC engineers and how these compliance guys are paid so much? Okay. Well, getting product out the door usually means you're dealing with all sorts of conducting surfaces. And the way you have to model it is with, take into account the effects, is with image of everything above it. All right. So this is kind of a big deal. All right. That's for currents that are parallel. Now, if you have currents that are perpendicular, suppose I have I here, straight up, its length is still going to be L, and it's going to be like a distance above the ground. I'm not even going to bother showing you this. Well, here it looks like minus Q is here, and plus Q is there, right? Y'all see that? So I come down, whatever this distance is, come down that distance, put an image here of plus Q, and then I take this one down to here, and I put a minus Q here. And it goes from the negative to the positive, right? And you can see now, currents that are perpendicular image in the same direction. So if I have a current like this, there's in this perfect conducting plane where I'm standing, then the image would be the same magnitude, same direction, just below it. And then when I want the electric fields up here, or magnetic fields, the only thing I do is assume that ground plane doesn't exist, and I find it. And by the way, it will give the values for either the voltage or the electric, or the tangent electric field will be zero all around that ground plane. You can prove that. I'll just mention this briefly. If you think about this one, if you have a Q plus here, right? Come down to this point, and look, the electric field will be in that direction from that Q plus, agreed? Now, since we got an image down here, same exact distance away, right? Only this one will have an electric field in this direction, right? Mm-hmm. The horizontal components will cancel exactly. The vertical components will add. And that vertical component you could get the D field from by divided by epsilon naught, right? Or multiplying by it. If you take the E field and multiply it by epsilon naught, you'll get the D field. If you have the D field, you'll also have the surface charge density. Do you remember that? The D normal was equal to the surface charge density on a good conductor. Remember that. It's a real good thing to know, believe me, because a lot of times, especially if you're involved in building stuff and doing testing, we actually have to get product out the door. That's the way I think about it. You're going to be out there, and somebody's going to say, well, I wonder what the charge density is there, or the normal D field is, and you can estimate it very easily if you know the method of image. Very easy. And the reason I'm saying these kind of things is because I know this actually happens because I've had to deal with stuff like this, both surface current densities and charge densities, mainly current densities. When we did, I don't know if I mentioned this, but years ago, I was involved in a project. We're supposed to incorporate in the lectures real life experience. That's the reason I'm doing this, not the waste of time. on multiple launch rocket systems, yeah, right before the first Gulf War up in Huntsville. Well, it's called an MLRS system, multiple launch rocket system. They're just tubes, and they got long rockets that got 6 payloads that come out at different times. And they had to make sure, I might have given you this spiel too, I don't think I did, about lightning striking. Lightning striking any kind of a weapon system is a big deal, because if they go off, they got big problems. And lightning does strike systems because they're usually a high point in the desert. And if by chance there is a storm, all right, it will probably hit the metallic stuff out there. Anyway, so we're testing them. And we have the simulated lightning tester. They had a screen from the floor to about the ceiling, a little higher than the ceiling. And they put about a couple million volts on that. They had a capacitor bank they'd charge up. Huge capacitor bank. And it's called a Marks bank. They charge up to a couple million volts. And then they put that on this crosshatch grid. It was like a wire fence, thin wire fence at about 30, 40 feet above the ground. Huge thing, bigger than this room in terms of the screen. And then you put whatever you're going to test, the item under test, in the center of that. And you want lightning to strike it, simulated lightning. And the currents are immense, by the way. Real lightning, when it hits, gets a peak current of about 20 kiloamps. We had more than that when we struck. The thing is, our duration was shorter. With real lightning, it has a much longer duration. It's called the return state. Anyway, I did my PhD on the electric field transients related to the late time field signatures from lightning. Really, it was about nuclear weapons, but can't publish it. So anyway, when I was doing this stuff, it was modeling. It was a simulation of it. I learned a lot about lightning. I had to do all this reading because I had to become very familiar with the events I was going to be writing about in terms of what's likely the charge, what's likely the geometries, what's likely the environment and all that. So I had to do all this, underground as well as above ground. Well, with lightning currents, lightning is a pain in the butt to model because there are long strokes that we would think of. They have a lot of inductance in that. It's not easy to model. They have a much longer duration than something just from there to the ground. So there's ways of extrapolating what's going to happen based on your measurements. We had a much higher peak current, but a much shorter duration. Power was a little less than a real lightning stroke, but we had to have a contact point. Anybody want to guess how we made lightning hit a certain point on this thing? Now, this is primarily a dielectric outside tubes, but it had a metal frame. Very close. We took a paper clip and we unwound it and bent it up. I guess that antenna would be right. It was a contact point. And the reason we did this is anytime you have a sharp piece of conducting material, the electric field will be enhanced at the tip. I don't know if you know this. There's even a microscope called the field emission microscope. It has a super sharp point. And in a low vacuum, what actually happens is that tip, when you just put a low voltage, you get an electric field that goes up. And it goes up proportional to 1 over the radius of that curvature squared. Now, I'm not going to get, I can get into that if we got more time. If you want to see this, I'll do it after class. But what's really interesting about this, we just took a paper clip and we literally taped it onto the point we want hit with, I don't even remember what kind of tape we used, and then we bent it up. When the lightning's done, there ain't no tape left. And we bent this thing up to hit it. And the only way we could get measurements and get the information out was by a thing called a BDOT probe. That measures the time rate of change of the magnetic field. But to get the information out to where we could store the information, we had to use fiber optic cable, because any other cable would be completely messed up, coax or anything like that, because it would cause so much electromagnetic interference from the lightning event on the actual cable. So we had to use fiber optics to get the information out to the recording systems. And then we analyzed that. Anyway, when we were doing that whole thing, imaging is a big deal, stuff like this. Everything has to do with understanding basics, right? Basic physics, the electromagnetics. So, getting back to this, currents in the same direction image, or perpendicular, sorry. In other words, vertical currents image vertically. It looks, so if you have a half-wave dipole normally, and you want to use the ground as the bottom half of your antenna, you just need a quarter wave here, and I'll get to this in a second. All right, y'all with me on this? It still looks like a half wavelength. The only thing is, it only radiates power over one half of the space, and since it radiates power over one half of the space, it means the radiation resistance is actually half the real radiation resistance. Now, I'm going to get to that in a second. Here's the real thing. So based on what I said, suppose I had an antenna like this that had an angle, and this was the current I here. And I wanted to see how would it image? Well, you always go from the in straight down. So if this was height H, you'd go straight down H. Since this we can assume is negative, let's assume the current's going that way. This will image positive, right? Then you come from this one, let's assume this is, call this H1, H2. Since this is positive Q here, we come down H2. We make it minus Q. That's positive. You can see it's imaging like this, isn't it? And you'll notice the horizontal components are opposite directions, the vertical are additive, correct? And that's how you do it. And that's a good thing to remember if you're ever in the real world. And you have an antenna at a cockeyed angle, and you want to know the effect of the ground, right? And you guys are smart. You can deal with this stuff. The mathematics come to you once you understand the actual conceptual physics or the way to model it. So now we get into monopoles based on the method of images. When I teach electrostatics, I believe, did I ever teach anybody here electrostatics? Well, I usually go through the method of imaging. If we're solving differential equations, I show them the power of that because it's so useful and powerful in solving things. Okay. Now, we get into monopoles. Mono means one. A pole is usually a plus or minus. Here we're going to have current only in the positive direction or positive charge. Think of it that way. So for a monopole, here's how it works. If we have normally a dipole, this would be a dipole antenna. It's got a length L. You don't even have to worry about the length. It can be any length at all. If you have this antenna, whatever length it is, you're going to have two things. You're going to have a directivity, and this would be for the lambda, I'll call it that, dipole. You're going to have a directivity, and you're going to have a Z input. All right? I'll even break it down further. You're going to have a radiation resistance. Now, if you have, and this would be for a dipole here, now, if you want a monopole that radiates the same electric field's power, all right, in the upper half plane. Now, if you have a monopole, you need a ground plane, a good conducting ground plane. Examples of good conducting ground planes are the surface, the hood of a car. I mean, it's not exactly, but it's close. If you have most of your transmitting antennas, AM transmitting antennas, they're just above ground. I mean, they just have a single pole going straight up, and they have like a conducting ground plane that they create either by running wire mesh below there, or they've got a ground that's saturated with like copper sulfate or rock salt to make it very conductive. So all the currents are on the surface. And the antenna, the actual length of the effective length of the antenna is the upper length times 2. It's a monopole. That's what I'm going to tell you. Trying to think of other most of common examples of this, but you wouldn't know them. On the aircraft carrier Eisenhower, I was out there as a weapons consultant. We were doing electronic warfare. Just about everything mounted on the carrier, on most of the frame of the carrier, you could assume infrared ground, but I think we did stuff. I think. I'm just telling you some of the things I've experienced. So when you have a monopole antenna, whatever this length is, L, and you want the same exact electric fields, this length will be L over 2. Right? It's half the length of the dipole antenna, right? The electric fields will be the same. Then the directivity D for the monopole. Now this is a monopole. If this was like a half wavelength, this would be a quarter wavelength, and so forth, right? If that was a wavelength, this would be a half wavelength. Everybody with me on this? The directivity, if that is the directivity of the dipole, the monopole will be the directivity of the dipole divided by 2. And I'll tell you the reason why. Remember, directivity is actually equal to 4 pi, the integral from 0 to 2 pi. Technically, it's the integral from 0 to pi of the normalized power density times the sine of theta d phi. Do y'all remember that? That's the one we use to calculate the directivity. Well, we calculated that directivity, we assumed one thing. This thing's going to radiate from 0 straight up of the z-axis to pi with theta, right? But actually, if you have a ground plane, the radiation from 90 degrees to 180 is 0, right? Nothing's radiated. So that means this integral is exactly 1/2 of what it would be for a dipole antenna, which gives us exactly 1/2 the peak directivity. All right, y'all with me on this? Now, that's how come the directivity is going to be, I'm sorry, exactly twice the directivity, because the bottom of this thing is going to have half the value it did for a dipole. So if it's down by 1/2, the top part's up by 1/2, like up by 2, right? So it's going to have, I put this wrong. This should be 2 times the dipole. I'm so sorry. It's twice that of the dipole. I'm going to do an example of this. So if you think about this, let me give you an example. If you have a half-wave dipole over here, directivity is 1.64, right? Times the cosine of pi over 2 cosine theta over sine theta, that whole mess squared. Over here would be twice that. Or it would be, let's see, 1.32, right? I mean, sorry, 3.32, 1.6 squared times 1.6. So, or sorry, 1.6 times 2. 16 times 60, it's going to be 3.2 something, okay? So it's twice that, but it's the same form as it is, only its value is only from 0 to 90 degrees. And below that, directivity is 0. Nothing's radiated below there. Now, the radiation resistance, or Z, the actual Z input for this, will be equal to the Z input. This would be for the monopole. Z input for the dipole divided by 2. So for a dipole antenna that's exactly half wavelength, it's 73.2 ohms plus J 46.5, right? For a monopole, it would be half of 72.3, which is 36 point something plus J, then it would be 42.5 divided by 2, or 21.25, J 21.25. You with me on this, guys? Or the radiation resistance would be, instead of 73, about 36. All right, you remember, just remember that concept. Otherwise, the electric fields radiated up here are the same as they are for a dipole. The real deal is with the directivity and the radiation resistance. And if you look on his thing on monopoles, this is on page 462, it starts. And then 464, finally on page 466, if you have your books, he shows you, he catalogs things, and he has the symbol and everything to do with like a Hertzian dipole, a short loop or a small loop antenna, magnetic dipole, half-wave dipole, and quarter-wave monopole. The quarter-wave monopole, half-wave dipole are the same exact radiation patterns above the horizontal plane, assuming that thing is perpendicular to the conducting ground plane. You with me on that, class? If you got your books, you can see that. It's not hard at all. There's no real conceptual difference about what's going on if you have a certain monopole and you know the dipole characteristics that are associated with it. You can get anything you want. That's it. Are you all seeing that? I see most of you have your books and you see it. It's the only thing you need to know. That's it. Okay. And if I give you a few problems, it'll flesh it out. But the problems you're going to see are almost automatic here. If I ask for the electric fields from a monopole given a certain current, the only thing you do is find the electric fields from a dipole with that twice the length, right? Of a dipole with twice the length of that monopole. Scam like a bomb. No, I've never done this, but I've thought about it. You know how you get people calling? Call this number, right? Well, find the call this number thing. One of those numbers and give it to the other guy that's always bugging. And let them keep calling each other to it. Yeah. Drive each other nuts. Because, I mean, some of these guys, you know, it's not just hang up, change your number. Then after a while, they figure that out. So, I mean, start block that call, and then they'll start calling you from a different one. But as long as they got your number, they'll have 100,000 numbers they can call you from. And they do this electronically using the computer systems. Well, wouldn't you like to just, every single number that calls you, you call them with the other guy's numbers, all of them, and just let them waste all their time on each other. It'd be like a flood ping. You know what a flood ping is? How many do? You do?
I think so. It's where you separate everybody, right?
All right, flood ping back in the day where everything was allowed to be talked about was, it's basically an interruption services. What they'll have is something that is going to try to access a given IP address over and over and over again, so nobody else can access it at the same time. It's called flood ping. You're overwhelmed as soon as the thing comes in, and you're trying to decipher whether it's legitimate or not, and process the data. Another one's coming in, and nobody else can get through. It's called a flood ping or a denial of service. Well, with these calls, now I don't know, if you're going to allow them to call each other and they only have each other's cajillion numbers, then they're going to flood ping each other. And eventually they're going to go out of business. But I don't know if they'll ever do that. They're probably too smart. But it was something to think about for me. All right. So now after we talk about monopoles and halfway dipole, now we're talking about arrays. Now array antennas are so powerful because what they do is use constructive interference to greatly enhance the signal and the directivity. And they're fantastic. And I'm going to start by saying with array antennas, there are so many different types of array antennas. You can have one-dimensional array. And by array, I mean this. If you have an antenna element, you're going to repeat that antenna element all the way down every so often. So maybe every half wavelength, I'll have another half-wave dipole oriented a certain direction. Or I could have a loop antenna where that element is repeated over and over again. Now, the thing about this is the currents on these elements that we're going to do are going to be same magnitude, but there will be a phase change that is the same amount per element. I'll show you that. This is only one way to do it. In the real world in antennas, it's not just like that. They're two-dimensional arrays, not only this way, but this way. They're not just straight wire antennas. They're patch antennas or parabolic antennas, something like that. And they step and repeat until you have an array of them, periodic usually. In other words, they're usually spaced the same distance. Don't have to be both this way and that way. All right. So we're going to start with the most basic array and the typical one. We're going to assume we have a whole bunch of antenna elements, and I'm going to start with just isotropic elements. It means they radiate the same in all directions. And so I'm going to have a current here, I naught, a current here, and all the spacings are going to be the same too. And out. So we have I naught here, we have I naught here, and here's the difference. This one will have the same magnitude, but it can have a phase change. So this might be at 0 degrees. This is I naught e to the j 10 degrees, right? Next one's going to have a phase change too, but it will be progressive. Whatever the phase change is between this one and this one will be the same phase change between here and here. So it's e to the j2 alpha, and it's getting bigger, right? Next one will have a value I naught e to the j3 alpha, and so forth. And if this is the nth element, this was the first element, that was the second, third, and so forth. Then the nth element here will have a value of I naught e to the j, and then it would be n alpha. Y'all follow me? You want to know where that is in the book? On page 467 it starts. He starts with just two dipoles. I like to do the monopole case. He shows what I'm doing, only it's vertically oriented on page 470. And then on page 480, 473 actually is the one. He likes to do it vertically. I like to do it horizontally. It's easier for me. Are you with me, class? Now, this is the critical thing, the thing I'm about to show you, a couple things. The first is every angle is not measured with respect to Z. It's measured with respect to the axis of the antenna. So if this is the axis within the antenna, you can call it the Z-axis, but it doesn't matter. It doesn't matter at all. It's an axis that the antennas are placed upon. And it doesn't matter if these antennas are vertically oriented or they're horizontal. It makes no difference. The thing is, it's the axis that they're mounted on. Now, each one of these antennas has an associated electric field from it. Y'all with me? Always, it's going to have the same form. In other words, since I'm assuming these things are isotropic radiators, then if I come out, I'll try to do this consistent with Wentworth's book. I'm going to go out a distance r. Now, I got to explain something. I'm going to go way out there to a point, and I'm going to find the E field. So if I take this thing and I kind of scale it, if I looked at this, here's my array. I'm going to a distance r. And if this is the total length of the array, n times d, n would be the number of antennas, d would be the spacing, then r is assumed much greater than n times d. You're a long ways from it. Y'all with me on this? This is how you've got to do this if you're going to find array theory. So this is distance r, and here's the angle measurement. And I'll use phi for that angle. You with me, everyone? Now follow me on this. There's r, first one. The next one here will be related to that distance. This distance will be r. This is going to be, and I'll call this, that's, say, r naught. Here, r1 would be equal to r naught, but it's less. Now take a look at this distance. Can you all see? We're assuming these things are in parallel. That ray is in parallel with that ray that's pointing at a point way out there. It's parallel with that, parallel with that. They all end up at the same point, parallel to each other. So this distance would only be, it would be equal to r naught, but it would be minus this distance. Do you all see that? And you see how that distance right here is going to be r times the cosine of phi? Because here's, I mean, it's so r minus cosine of phi times d. D would be here, right? And if phi was equal to 0 degrees, then d would be the difference, right? Because if you look in this way. So this is r naught minus d times cosine of phi. Now what about this r2 here? Well, that would be r naught minus 3 times d cosine of phi. You all see what I'm doing? The reason I'm saying, sorry, 2. And this one, r3 here, would be equal to r naught minus 3 times d cosine of phi, and so forth. You can see that each one of these things, like the distance difference here or here, is simply going to be the cosine of phi times the actual horizontal distance difference between that element and the first element, right? It's going to take that and then subtract r naught, subtract that from r naught. Okay. Y'all give me that? All right, now, here's the deal. When you're assuming isotropic radiators, then you're assuming the electric field, this is just for the purposes of getting to the bottom line. We're going to replace this in a second. We're going to see E iso is some K over R. All right, and it'll be E to the minus J beta R. That's going to be the form of the electric field, and you don't even have to worry about the polarization. You can just call it A phi for now. Doesn't matter. We're assuming this thing, they're all going to have the same polarization, to be additive. This is isotropic. The reason it's isotropic, it doesn't vary with angle. You see that? If you calculate the power radiated from that, the power density from this, 1/2 times E squared over 8 it does not vary with angle. Therefore, it is, by definition, isotropic. If I have that, and I want to see the electric field at a given point, and this is important to see this, I'm going to say the total electric field from this array would be the electric field from the first one. You all see that right there? And it's at a certain given angle, so it's going to be equal to simply I naught over R right there put K? How about if I put K I naught? That'll make it a little clearer. K I naught times e to the minus j beta r. The next one's going to have the same form, K I naught, but it'll have e to the j alpha, the phase difference, e to the minus j beta, and here it's going to be r minus d cosine of phi. And this whole thing is divided by that r minus d cosine of phi. But I want you to show this because you're a long way away. R1 will be approximately equal to R naught, will be approximately equal to R2 in terms of a 1 over R. Do you all see that, class? With me? If R naught is 100 and D is 0.1, then it makes sense because 1 over 100 is about 1 over 100.1 is about 1 over 100 or 1 over 99.9, right? It's about the same. So you can just leave this as R. The next one is going to be plus K, then it would be I naught e to the j 2 alpha, then e to the minus j beta, and here it's going to be R minus 2d cosine of phi over R, and you can continue, right? Now, a question that should come to your mind is, well, how come you didn't put just R here? And the reason is this. You see that beta? That beta is 2 pi over lambda. And every time this changes by the order lambda, it repeats itself. And that's why even though the R minus d cosine theta in magnitude is about equal to R, yet if in terms of wavelengths, it's many, many times R, then you've got to worry. You'll see this in a second. Now, you all see how this is going to progress, right? The next one would be K I naught e to the j 3 alpha. I'll write this one more. It'll be plus K I naught e to the j 3 alpha times e to the minus j beta. And here we have R minus 3 d cosine phi over R. And then I can put plus dot 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 plus K I naught e to the j n alpha times e to the minus j beta R minus n d cosine of phi all over R. And that would be the series. Now below, y'all see, I'm just trying to show you the progression. I'm going to come over here and I'm going to say, in fact, if I go ahead and I multiply this e to the minus j beta r, I'm going to multiply this together. I would get e to the minus j beta r times e to the plus j beta d cosine phi, right? Y'all see I can do that. And that's what I'm about to do right here. So now I'm going to say the total E field is equal to, I'll take the K I naught over R out in front. I'll take e to the minus j beta r out in front. And now I'm left with this. I have the first term is 1 plus, then it's going to be e to the minus j. Oh, by the way, you see how I have a j or 2 there and a 2 there? It would be a 3 there and a 3 there. Y'all see that? So now I'm going to put e to the minus, or e to the, plus j, because it's going to be minus j beta times minus is going to be plus, right? So it's going to be e to the plus j alpha plus d cosine of phi plus, and then it's going to be e to the j then e to the j2 times alpha plus, it should be beta d, pardon me, beta d, right here. Beta d cosine of phi, and this should be plus beta d cosine of phi plus e to the j 3 alpha plus beta d cosine of phi plus dot 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 plus e to the j n times alpha plus j beta d cosine of phi. Y'all see what I'm doing here? I'm getting it in a form that's easy to catalog and manipulate. Now, the thing that's reoccurring over and over again is this alpha plus j beta d cosine of phi. You agree? So what we do, and that's what I'll do here, is now we create a new term. We call it psi, capital psi. We use a lot of Greek letters in physics and electromagnetics and math in general. So let's say let psi be equal to beta d cosine of phi plus alpha. This is just to help the bookkeeper. Now, coming back to this, what I've really got for my E total is equal to, you see this right here that I broke out? That's the isotropic elements electric field. Do y'all see that? So what I like to do right here, I can just say it's the electric field of the element. If these are all the same, it would be whatever the electric field is of the element, ELM, ELEM. Then it's times this mess. And this mess is really can be written as a summation. From n equals, I can go from 0 or I can go from 1 to n, or 0 to n minus 1. Now, I better go, from 1 to n. I gotta make sure, try to be consistent with this book. Oh, he doesn't even show how it's done. I'm going to show how it's done.
What is that subscript of E in the bracket?
It's just element ELEM. I'll write it a little larger. How's that? Matter of fact, let me do this. I'll put it right here. E total, right there, is equal to E of the elements. It's for each. All right. Then it's going to be times the summation, all right, from n equals 0 to n minus 1. And here, what you have is, if you look, since I've taken this, right, it's just going to be e to the j small n times psi. Now, if you look at this, psi is alpha plus j beta d cosine of phi, and when e to the j, when n is 0, it's just e to the 0, which is 1, right? Which is this first term, which would be here when n is 0, right? And then I would go, I have n elements from 1 to n, so I go all the way out to here. You agree with this, class? All right, now if you look at this, right here. To evaluate this, we've got to evaluate this. And here we've got to get a closed form, and that's what I'm going to do. I'm going to do it right over here. Did anybody have any for signals since you did? You remember this probably. I do this and I make a big deal out of it. All right, so if I have a summation of a to the n, from n equals, I'm going to go from 0 to n minus 1. Usually it's from Q1 to Q2, but I'm going to do it this way. Actually, let me make the top one n. You'll see why in a second. I'm going to do it this way. So this is just I want to know what that series converges to. What the value is, right? So I'm curious about this. Well, I want to know what that is. Well, that would be equal to a to the 0 plus a to the 1 plus a to the 2 plus dot, 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 plus a to the n. Y'all agree with that? Now I'm going to take that same series, I'm going to multiply it by a. So now this would become a to the 1 plus a to the 2 plus a to the 3 plus dot, 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 plus a to the n plus 1. Y'all agree with that?
Mm-hmm.
And now I'm going to subtract this from the top one. So I got the first series, and here's my second series, and now I'm subtracting. Y'all see this? So here I got a to the 0, I got no a to the 0, I'm subtracting. And by the way, what I'm actually doing is this. I have 1 minus a times the series from n equals 0 to n of a to the n. If you look, this is what this is going to be, isn't it?
Mm-hmm.
Right? Well, I got a to the 0 minus, there ain't no a to the 0, so I've got a to the 0. Then I've got a to the 1 minus got an a to the 1. It's gone. I have a to the 2 minus a to the 2. It's gone. A to the 3 minus a to 3. It's gone. Right? A to the n, there's an a to the n down here. It's gone. But there's no a to the n plus 1, right? So it's a to the 0 minus a to the n plus 1 would be what this series converges to. Do you all agree with that? You see the reason. Mathematicians are good at these tricks. I call them tricks, but they're just being very clever with the way they manipulate things. Now, if I take both sides and I divide it by 1 minus a, now I have a nice closed form to what that series goes to. Do y'all see that? Math, did you have series in mathematics? Maclaurin series, binomial series, all? If you know one thing about series, if he does the proofs, it's really being clever and manipulating. Have I ever told you the story about Gauss, one of the greatest mathematicians? And he's a physicist. When Gauss was like in 3rd grade, I remember this in a math book when I was real little, like in 3rd or 4th grade. Gauss didn't like wasting time. So he was in 2nd or 3rd grade. And what the teacher would do is give them something and take them about 15 minutes to a half an hour, and he'd go do something. So they asked him to add all the numbers from 0 to 100. All right? And say you go 0 plus 1 is 1, plus 2 is 3, plus 3 is 4, plus 3, and so forth. You're just adding them all up, right? Gauss wasn't going to sit around doing that. He reasoned with himself, I have 0 plus 1 plus 2 plus dot, 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 plus 100, right? Said, but that's interesting. If I write them backwards, I get 100 plus 99 plus 98 plus dot, 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 plus 0, right? Now, if I add these two columns up, I get 100 plus 100 plus 100 plus 100 plus dot, 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 100, right? Or I have 100 times 101. Gauss knew how to multiply. But that's twice the answer. So he divided that by 2, and he got the answer, and he walked up. This is a very famous thing, by the way. When you're a young kid and you see this, you really admire that kid. He saved himself a lot of headaches. He went up and he handed it to the teacher, and that's the old trick the teacher knew. The teacher was shocked. So she took Gauss to somebody at a university, and they realized his capabilities and how he is a true savant. And then Gauss kind of skipped through a whole bunch of grades real quick. But anyway, that's the truth. Really, if you're adding numbers from 1 to n, you take n times n plus 1 by 2, and that's the answer. But these are all these manipulation tricks. This is a little trick. It's a series. So anyway, if you have a geometric series, a to the n, this is what it will become, it'll fall out to, all right? Now, we don't have a to the n. What do we have? We have e to the j n psi, right? So if you look at this, can't I write this series? I can say that e to the j n psi from n equals 0 to n minus 1 is really the summation of the quantity a to the j psi to the nth power for n equals 0, n minus 1. Do you all agree with that? Right? That, or I should say e right here, I'm sorry. It would be e to the j, e to the j psi, right? And that e to the j psi is like a over here, right here. You see that? And therefore, this series right there, that I'm showing you, the summation from n equals 0 to n minus 1 of e to the j n psi simply manipulates to this. 1, a to the 0 would be 1, minus e to the j, and now it'd be capital N psi. The reason is my limits go to n minus 1. So if I add one to that, I get e to the j n psi on top over just 1 minus e to the j psi. The reason I'm doing that is I'm trying to manipulate this. Are you with me? We're almost there. Give me a second. Finish this. Now, this doesn't, I look at that, I don't see anything that's useful. Remember it now? Okay? So now what I end up doing is anytime I have something minus e to the j something, I always think trig identities. And I know that's starting to look like a sign to me. So I'm going to rip out e to the j n psi over 2. You're going to have to just hold on here. This thing, when I have 1 minus e to the j n psi over 1 minus e to the j psi, I can go ahead and factor out an e to the j n psi over 2 out of the top, and I get e to the minus j n psi over 2. Then it would be minus e to the j n psi over 2. And on the bottom, I can manipulate e to the j psi over 2 up front. And I have e to the minus j psi over 2 minus e to the j psi over 2. Now, I know it's late. I'm just going to try to close up here. Remember what the sine is? The sine of theta was equal to e to the j theta minus e to the minus j theta over 2j. Do y'all remember that? That's Euler's identity, right? So that's Euler's identity. If I multiply by 2j, I get this, right? With me? Now, if I put a minus sign, I make that minus and that plus, right? And now if I let theta there become psi, look what I have. or n psi, right here, n psi over 2. So what I'm going to tell you is the bottom line on this is this will be e to the j n psi over 2 over e to the j psi over 2. And then it will be times, just write this down, times the sine of n psi over 2 over the sine of psi over 2. And lo and behold, this is important, and I'm going to talk about that, but I wanted you to see how you get there. And I'm going to give you some information when you go home. I'm going to say that's the key, because see, I know what a sine function looks like, right? And I'm going to make the argument next time that this function, if psi is small, looks, the sine of x is about x when you're at x small. So this is starting to look like a sine x over x or a sinc function, right? And I'll bring that about, and then I'll show you some things that are really interesting, and we'll take a look at arrays. I am sorry I was so tired. I've been tired lately in this class. Wow, I apologize. I will do better. You guys hung in there. I'm 3 minutes over. But I think stories I told, there were at least 3 minutes. I want to thank you again for recording that lecture. Does anybody look at the recordings? There. I cannot thank you enough for that. You know why? Because